Okay, hello, you're welcome to my channel. Now in this video, we want to talk about existence of limits, right? Okay, great. Right, if you've not subscribed to my channel, please do what to subscribe and turn on the notification buttons. Okay, let's get started. Now suppose we have a function called f, okay, and that function is defined in an open interval containing a point c. So what mean by function and definition of function is that suppose we have a function, all right, and the domain of that function is an open interval, okay, containing a particular point inside, okay, a particular number inside, and that number is called c for any arbitrary number. Okay, and let's say that function is not defined at c exactly, but it is defined in an open interval or in the surrounding of c, or in every other number that is closer to c. Okay, then the limit of that function, okay, written in terms of x, as x approaches the point c, is said to exist if the following, okay, if the following equation is true, that the limit of f of x as x approaches c from the left is the same thing as the limit of the function as x approaches c from the right. And the result of that limit is going to be a real number L, a unique real number L, if the left-hand limit, okay, this is what we call left-hand limit, that is, as x tends to c from the left, we call that the left-hand limit, all right? And as x tends to c from the right, we call that the right-hand limit. So if as x tends to c from the left, if it is the same thing as x tends to c from the right, and that same thing is what we call L. So that real number is the limit of that function as x approaches c. So you can see a point, let's say this is the x-axis, okay, and then this is the interval, let's say from point A to point B, okay, it's an open interval. Then this is a point C, lying inside the open interval, all right, and we say that this function is defined in this interval, okay, is defined at every point in this interval, except possibly at C. It may not be defined at C, all right? Okay, so let's say the function is not defined at the point C. Good. Now, we are saying that the limit of this function exists if, as we approach C from the left, the result of the limit is the same as when we approach C from the right. And the common result, or the common value we get, is the real number L. Great. Now, I will not just leave here. I'm going to give you examples so that we apply the definition accordingly, all right? All right, let's get into it. And now, on the left part of the board, we have a table, okay? But first of all, we have a function, x squared minus 1 over x minus 1, and we want to take the limit of that function as x approaches 1. So let's make a little bit of a comparison. We have, in general, we have the limit of a function as x tends to a value or a number c. So here we have the limit of this function, okay? So the function now is x squared minus 1 divided by x minus 1 as x approaches 1. So that 1 there, maybe I should put it in blue, is the value we are approaching, okay, which takes the position of the c. Good. Now, but at first, if you want to look at the domain of this function, you will see that the domain of that function is every real number except the number 1. That is, the function is not defined at 1, because at 1, the denominator is going to be 0, right? Good. So that tells us about this information, that the function is defined at the point c, but it may not be defined at c, all right? So this function is defined everywhere in the real number system, but it's not defined at 1. So you want to see how the function behaves as we approach 1. Okay, good. So I've set up a table. This table has the input x value and the corresponding output. That is, when you have x to be 0.9, you plug it into the function, you evaluate it, and you get your corresponding result, all right? Good. Now observe, as we approach 1, you know, to check if this limit exists, we need to look at the left-hand limit, that is the limit of the function as x approaches 1 from the left, right? The limit of that function as we approach 1 from the left, okay, to check if it is the same thing as the limit as we approach 1 from the right. Good. So we're going to observe that. So we're going to have to look at the left-hand limit and the right-hand limit, all right? Now, if you're approaching 1 from the left, look at this number 1, all right, on a curve, on a graph like this. This is 1. So let's say we are approaching 1 from the left. That is, we are looking for real numbers, okay, closer to 1. That is what we're looking at. So as we are approaching 1 from the left, let's see what we got. we have 0.9 will be those numbers that we are going to be talking about, all right? So if you come here, 0.9 is here, plug in 0.9 to the function, what do we get? We get 1.9. The corresponding result is closer to another number 2, right? So if you have 0.9 here, the result gets closer to this number 2. We plug another number which is very close to 1 from the left, 0.99. The corresponding result is very close to 2 from below, all right? Good. That seems as if the result of the limit as we approach 1 from the left is going to be 2. In fact, let's just say as we approach 1 from the left, the result of the limit is 2. So let's say f of x. Okay. And now we have to look at what we get when we approach 1 from the right. So this is 1, that was from the left. It seems as if we're going to get 2 because the numbers we're getting closer to 2 as we're getting closer to 1 from the left. So from the right, as we are getting closer to 1 from the right, that means we're talking about numbers bigger than 1, but lying very close to it. For example, 1.001, right? Maybe let's start off with 1.01. So when we plug in 1.01 into that function, what we get is 2.01, getting closer to 2 from above. Okay, so this one was getting closer to 2 from below, while here we are getting closer to 2 from above. So you can see what we've got, that as we get closer to 1 from above, okay, from the right, we are getting closer to 2 from above. That is 2.01 and 2.001. So it seems as if the result of the right-hand limit is still going to be 2. So since the left-hand limit and the right-hand limit have the same limiting value, okay, so it tells us that this equation has been satisfied by that function, that is the left-hand limit is the same thing as the right-hand limit, which is equal to the real number L. In this case, it is equal to the real number 2. So we can conclude that as we approach 1 from the left and from the right, the result of the limit approaches 2, okay, for both cases. Great. So maybe we can do this. All right. Now, I'm not done yet. You have to look at this function, okay, and observe it. If you want to plot this function in the graph, how would it look like? Okay. Well, looking at that function, x squared minus 1 divided by x minus 1, we can do some factoring on the function, right? Because the numerator is a quadratic, a reducible quadratic. So we have x squared minus 1. To factorize that, I'm going to factor that into 2. Okay, it has 2 factors. That will be x minus 1 times x plus 1, that is just the numerator, divided by x minus 1, which is what we have in the denominator. So we see that this factor and this factor are the same. Okay, we can cancel them. We can cancel them because x is approaching 1. X is not equal to 1. Okay, it is approaching 1. Good. That means this cannot be 0. All right. So when we cancel those, we are left with just x minus 1. So what I've just done there is like rewriting this function, that function, okay? So I've rewritten the function, what we have is x plus 1. So I've rewritten the function, and what we enter with here is just x plus 1. X plus 1 is the same thing as that function. Now, this is another function entirely, okay? And the graph looks like this. Just a straight line, okay, that passes through 1 on the y-axis. But what we have here is that function is, if we want to plot that function on a graph, okay, we are going to plot the same straight line, but the difference is going to be in the domain. This position 1, the function is not defined at 1. That means that when we get to 1, we are going to leave a circle, okay, just a jump stuff, okay? So we just jump that point and move on. So that function x squared minus 1 divided by x minus 1 has the same graph as this function x plus 1, but the difference lies in the domain of those two. Good. So if you are given something like that, what you need to do is to factorize it, and then you are going to reach this point, you just substitute. But note that that function is not defined at 1. So the curve will look like this, but except possibly at 1. Except at 1, actually. Okay, great. All right. So this is what it means for a limit to exist when the left-hand limit and the right-hand limit, they both give you a real number. They both give you the same real number. Then we say that the limit of that function is equal to that real number. Okay. All right. Thanks for watching. Please subscribe to my channel.